Okay, as we already know, what component that cause the power factor to be leading or lagging, so we should do a correction because as I mentioned earlier in this class, if the power factor less than 0.85, there will be penalty that company must pay. Okay, so most domestic loads such as what we have maybe in our house is a inductive load. Okay, it's a inductive load. Okay, inductive load means it is an L component. Okay, so what does an L component do to the power factor? I like we refer to the previous slide. Okay, this is inductor. We have inductor. So you can see that current lags voltage. Okay, if we have L component. Okay, which we can find L components in washing machine, air conditioner, refrigerator, industrial unit, induction motor. So we have lots of motor industry. So it contribute a lot to the uh, towards the to reduce the power factor. Okay, so it can operate at a very low, below than this one, below than 0.85. Uh, so how to improve this one is we need to bring the power factor up. Okay, for example, maybe from this previous example where the power factor is only 0.5. This is very bad. How to bring this 0.5 to 0.85? Okay, 0.5 for example, bring to 0.85. Okay, we already know that if we have a capacitor. Okay, if we put back capacitor, the power factor will be leading. Okay, so we can use capacitor to pull the power factor from 0.5 to 0.5. So okay, this is what we call power factor correction to improve power factor from bad power factor to a good considerable power factor. Okay, as shown in this figure here, place a capacitor in parallel with the load. Okay, we have industrial motor, put required number, certain number of capacitor to improve the power factor. Okay, the effects of adding capacitor can be illustrated in this figure. We can reduce this angle, the angle. Okay, as you know, this is V and I, and this is a real. So if we take a look on this power, this is imaginary, this is real. Voltage, this is P. We want to reduce this component, okay, this Q component. Okay, reduce it so that the angles become smaller and will contribute to a better power factor. Okay, okay, we can imagine it in this triangle. This is the real power, the real work, and Q1 is the original reactive power. We want to reduce it to Q2. Okay, we want to reduce from Q1 to Q2. How to reduce it? We need to add capacitor so that it can compensate or reduce the value of Q so that you can reduce the theta. Okay, the smaller, as you know, the smaller the theta, the higher the cos theta value. Okay, you see, this is theta angle, this is the cos theta. So the lower the value, the higher the cos theta is. So actually we only consider this part. Okay. 0 to 1. The profit is only from 0 to 1. So only between 90 degrees. Okay. So this is original equation, the P equation and Q equation. Okay, this is original. Q1 is S1 sine theta or P tan theta 1. Okay, if we choose to increase the power factor from cos theta to cos theta 2, from cos theta 1 to cos theta 2 without altering the real power, then the new reactive power is Q2. Okay, this is new real power equals to P tan theta Q. Reduction in the reactive power is caused by shunt capacitor. So QC here is Q1 minus Q2. Looking at QC, okay, the difference between these two, between Q1 and Q2. So it is a P tan theta 1 minus tan theta Q. Then we need to calculate the value of capacitance C required. C equals to Q C over omega V RMS square. Then QC, okay, is from this equation is P tan theta 1 minus tan theta 2 over omega V RMS square. Okay, we must note that the real power dissipated by the load is not affected by the power factor correction because the average power due to capacitance is 0. Okay, this is average power due to capacitance is 0. Although the most common situation in practice is that of an inductive load, it is also possible that load is capacitive. That is, the operating power factor is a leading power factor. In this case, the inductor should be connected across the load to do the power factor correction. Okay, let's take a look on this example 9. We have a 120 VRMS voltage source with 60 Hz and a load absorbed 4 kilowatt at the lagging power factor of 0.8. Find the value of capacitance necessary to raise the power factor from 0.8 to 0.95. Okay, this is the original power factor is 0.8. So cos theta 1 of 0.8 is 36.87 degree. And the reactive power Q1 is S1 sine theta. Okay, this is S Q T theta here. Yeah. So you know that this is triangle, so Q equals to S sine theta 1. P equals to S cos theta 1. Okay. So you can find Q1 is S1 sine theta 1 and S is 5000 sine 36.87. So we get the Q1 is 3000 VAR. Okay. Okay. So the new power factor is 0.95 and cos theta 2 of 0.95 is 18.91 degrees. Okay, so we have the new theta 2. Okay, this is the old one. This is 36.87, and the new one is significantly reduced in this area. Okay, it is 18.19 degree. Okay, this is Q2. This is Q1. So we need to find the difference. Then the new apparent power is 4210.5 VA. Okay, the new reactive power is 1314.4 VAR. So find the difference between Q1 and Q2. Q1 is 3000 and Q2 is 1314.4. So the difference is 1685.6 VAR. Okay, then use this equation to determine the value of capacitance needed, which is eventually becomes 310.5 microfarad. Okay. Actually, in real case, we don't use this capacitor value. We use this one. Okay, so you already know if this value is referring to this capacitor value. Okay, so it's not a very specific like this 1685.5. It's not like this. Okay, so it's somehow instead of 5 m bar, okay, it's mega var, like 10 m bar, then 20. So we have several capacitor and we will combine what is the best combination to improve the power factor in a power system. Okay, you can try this example, and the answer is here. That's all for this chapter. Thank you.